All right, these are thoughts and examples on section 5.4 from your book, which starts into exponential functions, more specifically e to the x. So let's go ahead and get started. First off, I want to show you something. It's a little beyond the scope of our class. And feel free to test this out, maybe on a calculator, to see the truth of it. But let me write that a little bit better. E to the x can be exactly represented by an infinite series that looks like this. 1 plus x squared over 2 factorial. You remember that factorial means basically the product of that number times the integers, I should say, times the whole numbers below it, not including 0. And then the next term is x cubed over 3 factorial plus x to the 4th over 4 factorial plus ... You can see how that goes. So if we were to differentiate this, let's differentiate both sides. The derivative of e to the x equals, let's watch what happens. The derivative of 1 is 0, so we're just going to have that term drop out. The derivative of x is 1. If you differentiate x squared over 2 factorial, well, the 2 that comes down will cancel with that 2, and you're left with just 1 there. So it would be x. Here's where it gets interesting. Don't forget that 3 factorial is really 3 times 2 times 1. So when you bring this 3 down, that cancels with that 3. You're left with a 2 up there and a 2 down there. So x squared over 2 times 1, well, that's 2 factorial. The pattern continues. Check this out. 4 factorial is 4 times 3 times 2 times 1. The 4 comes down, and that cancels with that 4, so you end up with x cubed over 3 factorial. Can you see the pattern that's developing? If I differentiate this infinite series, then I end up with the exact same thing that I started with. So in a very intuitive way, I suppose, this is a way of showing that the derivative of e to the x is really just e to the x. And of course, if you want to, you can prove that e to the x is equal to this infinite series. And of course, if it's an infinite series, you're going to have to stop it somewhere where you can at least see that it's close. And if you keep going, it's going to just get closer and closer. So anyway, just maybe an interesting way of looking at that. So this is kind of an interesting relationship. Basically what that's saying is that the slope of e to the x is equal to the value of e to the x at any point. Let's take a look at the graph of e to the x with your x-axis and your y-axis. E to the x graphs is just a typical exponential. Goes through the point 0, 1 and is increasing at an exponential rate from left to right. Okay, and sometimes you'll have a composite function. So the derivative in terms of x of e to the u, where u is some function in terms of x, that's equal to e to the u times u prime. Or you could also say equals e to the u times du dx. Same thing. So it's just a chain rule. I don't think that's anything too different than what you're used to, other than it's involving this e to the x stuff. Okay, let's work on some examples, and as always, I encourage you to work on these examples on your own. And if you I'll pause the video, check yourself, I think you'll find that you'll have good success with this stuff. Okay, number 1. Notice it's e to the u, so the derivative of f of x, f prime here, is equal to e to the u times, now notice that the multiplication happens down here on the base level, not the exponent level, times the, oh goodness, I left something off. How about e to the 3x squared minus 8? There we go. Times the derivative of what was on the inside, so the derivative of 3x squared minus 8 is 6x. And that's it. All right, I'd say with number 2, should probably rewrite just a little bit. So let's write h of x is equal to e to the negative 3 times x to the negative 1. Okay, so h prime is equal to e to the u times u prime. So u prime would be positive 3 times x to the negative 2. All right, so let's do some applications of this from some old stuff that we've done. So for number 3, let's find all local extrema. And this is an excellent time to review. Hopefully you're keeping up with your take-home quizzes and everything like that. And you should hopefully remember how to do this. So where do local extrema occur? Well, local extrema, and the key word in there is local. Local extrema always occur at critical numbers. And let's remember what critical numbers are. They are where f prime equals 0 or where f prime does not exist. Once you found those critical numbers, then you either use the first derivative test or second derivative test to show you what is a local maximum or minimum or potentially an inflection point. Okay, so if we're going to find critical numbers, in which that's where f prime 0 does not exist, we have to find f prime first. Little pitfall in here, of course. Did you see the product rule? Hopefully you did. Product rule. So it's going to be 1 d2, right? Derivative of e to the x is just e to the x, plus 2 d1. Derivative of x is 1. Okay, well, let's set that equal to 0. That will enable us to find our critical numbers. In order to make this work, we write 0 equals, factor out in e to the x, we're left with x plus 1 on the inside. Whenever you have a product, two different factors, and the answer is 0, use the 0 product property, which states that one or both of the factors could be 0. So we set both factors equal to 0. And if you remember that graph earlier of e to the x never crosses the x-axis. So there's no way that e to the x could equal 0. So we're simply left with x equals -1. So that's our lone critical number, critical value there. So, I don't know, let's do the first derivative test to help us figure this out. So to do the first derivative test, we're going to do an f prime sign chart with -1 being our critical number. So let's try maybe 0 off to the right. I think 0 will work. So if we try out 0, off to the right. If we try to 0 here, if I plug in a 0 into f prime of 0 would equal 0 plus 1, right? E to the 0 is 1. I'll write that out for you. 0 times e to the 0 plus e to the 0. So that would equal 1. And more importantly, it's positive. Let's go ahead and do -2 for the other side. F prime of -2. Oh gosh, we'll probably need our calculators for this, and I don't have mine with me. -2 e to the -2 plus e to the -2. So that's 1. So it's going to be -e to the -2. We don't really need our calculator. E is a positive number. Raised to a negative value makes it smaller, but still positive. So the negative on the front makes the final answer there negative. So we'd write maybe a final statement. We'd say f prime changes from negative to positive at x equals -1. Therefore, x equals -1 is a relative minimum of f. Okay, number 4. I threw number 4 in here. I realize it's a limit. It's been a while since we looked at limits. There's probably a good reason to look at limits. But I want you to notice something. This is a very, very special limit. Obviously, if you try to evaluate, you get 0 in the denominator right away. Obviously, that's a problem. Like I said, this is a very special limit. Let me write the general form of this limit. Limit as h approaches 0 of f of x plus h minus f of x all divided by h. You recognize it. I hope you do. This is the definition of the derivative, right? You recognize the difference quotient. The limit is the denominator approaches 0. This is the definition of the derivative. So more specifically for this problem, this is the definition of the derivative of e to the x. And the derivative of e to the x is e to the x. So your answer is just e to the x. That type of problem is very common on the AP test. I'd be willing to bet that you'll see something like that on the AP test. Something or very, very similar to it. Okay, we talked about derivatives. Let's integrate. So if you go back to that infinite series that I showed you earlier for e to the x, if you integrate that, you end up with the same thing. So here's that infinite series again. Again, if you want to prove it to yourself that that really does, or that really is equivalent to e to the x, it's fine. That would probably be a cool thing to do. So if you integrate both sides, here's how this works. The integral of e to the x then would equal the integral of 1 in terms of x is x. The integral of x in terms of x is x squared over 2. And you know that 2 factorial is just 2 times 1, so we could easily just put 2 factorial there. Here's where it gets interesting. The integral of x squared over 2 factorial would be x cubed over 3 times 2 factorial, which is really just 3 factorial, right? And let's just do one more. The last one here, 3 plus 1 is 4. You multiply that in the bottom, so it would be 4 times 3 factorial, and that's really just 4 factorial. So if you integrate e to the x, you end up with the exact same pattern there. So we can safely say that the integral of e to the x is just e to the x, and then don't forget the old plus c, if necessary, if it's an indefinite integral. Okay, and then if you have the composite scenario, you know, kind of like reversing the chain rule, you're going to get e to the u plus c. But remember that this pattern here, e to the u du, sometimes is a little more challenging than what might first appear. You're going to have to either do u substitution, or you're going to have to fix the problem with the chain rule. So let's take a look at number 1. So notice that number 1 is the integral of e to the u. And so let's do this using u substitution. So remember that if you're going to set up u substitution, u has to be the function that was on the inside. And the function on the inside is 3x plus 1. That's what's been plugged in or substituted into the e to the u function. All right, so then let's do du. Du is equal to 3 dx. So if we want to start substituting here, I would say we clearly have e to the u. So we've dealt with this. Now we still have that dx hanging out there, and of course we can use this to help us with that. The 3's cancel out, and you get dx is equal to du over 3. So I'm going to write du, and then the over 3 goes out there. All right, so integrating the integral of e to the u is just e to the u. Don't forget your plus c. Last step is to plug the x back in, or the x term back in. So it'd be e to the 3x plus 1 plus c in there. Of course, the 1/3 stays. These are very easy to check. If you wanted to check this, just differentiate, and you should end up with what you started with. I'll let you do that if you want. Okay, number 2 brings up a couple of somewhat interesting concepts. What I would do with number 2, before I looked at anything in regards to u substitution or anything else, this 5 right here, this constant, has a tendency to kind of muddle things up a little bit. So what I'm going to do is I'm going to take it out. Remember, you can take any constant factor out of an integrand and put it on the outside. And the only reason why I do that is that tends to make things a little more clear when you do the u substitution. Okay, so let's do the u substitution. When we do this, u, as mentioned before, has to equal what's on the inside. And the inside function is negative x squared. Again, just a reminder, feel free to pause the video, try these on your own, or if you get lost, rewind the video, try it again, and see if you can do it. Keep working at it until you can do it on your own. All right, so du then would equal negative 2x dx. All right, don't lose the 5 on the front. So now we're going to try to substitute u equals negative x squared, so we get e to the u. So we have substituted in for this. We're still left with x dx. I'm sure you can see over here that if we just divide both sides by negative 2, we end up with du over negative 2 equals x dx. So du goes here, and I'm going to put the over negative 2 out there. Okay, so to finish it up, we integrate e to the u, and we get e to the u. Don't forget plus c. And our last step would be to plug in the expression with x instead of u. So it'd be e to the negative x squared right there, and then plus c. Be careful about losing that negative 5 or the negative 5 halves as you continue on. All right, one more to go. Let's take a look at number 3. All right, number 3, again, using u substitution. For those of you who are good at finding the mistake with the chain rule and fixing it, feel free to do that. Personally, that's probably how I would do it, but I think the u substitution is much better structure. Okay, so u would have to be what's on the inside. So what's on the inside is cosine of x. We find du, and du is negative sine of x dx. All right, substitution looks like this. E to the u goes right here. I'm kind of lining these up vertically so you can see how they go. And then notice we still have a sine x and a dx there. Well, there they are. We just divide by negative 1. We can substitute that in for sine x dx. And I'll put the over negative 1 out here. Well, of course, that just makes it negative. All right, the integral of e to the u is e to the u. So we get negative e to the u plus c. So we substitute back in. We get negative e to the cosine x, and then plus c. All right, number 4 definitely looks a little more intimidating. If we do a little bit of algebra ahead of time, I think we can make it a little bit easier on ourselves. So let's do that. Here's what I'm proposing. Let's write, instead of e to the 1 over x, let's write it as e to the x to the negative 1. And instead of writing it over x squared, let's flip that up to the top and write x to the negative 2. And let's not forget our dx. The reason why I did that is just to get rid of fractions. Using negative exponents as opposed to fractions, as you know, typically makes life a little bit easier. Okay, so let's set up our u. U would have to be what's on the inside, and that's x to the negative 1. Du then would be the differential of that, so that would be negative x to the negative 2. Careful with that one. That one's sometimes kind of tricky. Dx. Okay, got a really straightforward substitution for u. So it's going to be e to the u. So this is taken care of. And then I've got x to the negative 2 dx. And of course you can see that right here, but we got the extra negative. Let's divide both sides by that negative 1. That cancels with that. So we're left with du, and then the over negative 1 comes out there. And like I said, dividing by negative 1, it just turns the whole thing negative. So when we integrate e to the u, we get e to the u. The negative is still there, plus c. So when we plug back in, we get negative e to the x to the negative 1 plus c. Okay, I think that might be it. Nope, we got some more to go. Good. All right, so I would say with number 5, we need to do some algebra to make this a little bit easier. Let's go ahead and go, instead of e to the root x, let's write e to the x to the 1/2. And then with that root x right there, let's move that up and let's make that times x to the negative 1/2. Let's not forget the dx. Okay, as we've done before, let's make u equal to what's on the inside. That would be x to the 1/2. Therefore, du is 1/2 x to the negative 1/2 dx. Let's try some substitution here. U is just equal to x to the 1/2, so this whole thing can be substituted as e to the u. Then over here, obviously we have x to the negative 1/2 dx left over. You see that over here on the right. Obviously the issue is the 1/2. So let's go times 2 on both sides. That means the half and the 2 cancel. So we get 2 du. So I'll put the du here, and I'll put the 2 out here. So integrating e to the u, I get 2 e to the u plus c. And we're left with, after substitution, 2e to the x to the 1/2. Let me put that on the right level there. Plus c. There you go. All right, looks like we have a definite integral coming up next. We do. Okay, so whenever if you have a definite integral and this whole u substitution thing, we usually just change the variable completely over to u's and we don't go back to the x's. So I'll do it from that perspective. Okay, so here we go. I'm going to write u equals negative x, right? The inside has to be what has to be equal to u. Therefore, du equals -1 dx. So I'm going to rewrite this as e to the u. And then, of course, we end up with du over -1. So I'll just write du here, -1 out there. But we've got to change the limits as well. So let's do that. So the two new limits, let's see here, u would equal, if I do the low limit first, it's going to be -0. So the low limit is still 0. And the high limit would be u equals -1. I'm just plugging in the 0 and the 1 here, right? That's -1. I'm sure you see we have a little issue here as far as how we typically do integrals. The limits are supposed to be the other way, right? The low one is supposed to be low, the high one is supposed to be high. So in order to flip those limits, which is what we're going to do, we have to change the sign on the outside. So this -1, of course, we've got to change the sign. So that becomes positive. All right, so the integral of e to the u is just e to the u. We're going to evaluate from -1 to 0. So that would be e to the 0 minus e to the -1. So e to the 0 is 1, and e to the -1 is 1 over e. So obviously we could evaluate in the calculator too, but that's what you get without the calculator. Okay. A few more to go. Number 7. Again, please do feel free to try these on your own and check your answer later. Okay, so u is a little more complicated, without a doubt. U has to be what's on the inside. So what's on the inside is right here. It's e to the x. So u equals e to the x. Therefore, du equals e to the x dx. Okay, so let's substitute here. I'm going to leave the limits off. We'll have to fix those later. On the inside, let's see here. What do we have? We have, let's see here, u is equal to e to the x, so I'd say we got u. Well, I'll tell you what, let's look at this a little bit differently. Just, I don't want to confuse you. Or myself for that matter. I'm going on low sleep right now. Okay, so cosine of e to the x, that's clearly cosine of u, right? And then when we look at this from what's left over, so obviously we've handled this. So e to the x dx, e to the x dx, that's just equal to du, isn't it? So I'm going to replace the e to the x and the dx with just a du. It's actually pretty handy, right? Okay, so let's go ahead and figure out our high limit and our low limit. Our old high limit was 0. So that would be u equals e to the 0, which is 1. So my high limit is going to go from 0 to 1. And then the other one was -1, so that would be u equals e to the -1. And we could just write that as 1 over e, maybe. So something like that. So let's integrate. Oops, let's not do that. Come on. There we go. So the integral of cosine is sine, evaluated from 1 over e to 1. Notice we didn't convert back over to the x's, right? When you have a definite integral, we change the variable and we stay with that change. We don't back substitute. Just easier that way. So it looks like I'm going to end up with sine of 1 minus sine of 1 over e. Again, it's going to be some crazy decimal. It's okay. We're just learning this process. Okay. Number 8. Integral from 0 to 1 of e to the x. over 1 plus e to the x. Now this is interesting. Hopefully you see this pattern. Hopefully you've practiced enough to see this pattern. But here's what I'm seeing. I am seeing a fraction, and I'm seeing that the fraction, the nature of the fraction is that the derivative of the denominator is in the numerator. You remember what that pattern is? Anytime you have the integral of u prime over u, essentially is what we're looking at. Of course, that's equal to ln of u, right? That's that natural log pattern. So let's just go with this straightforward. I don't want to get too far off track. Let's go ahead and just say that u is equal to 1 plus e to the x. Therefore, du is equal to e to the x dx. So I'll leave the limits off. We'll fix those in a minute. So this would be the 1 plus e to the x is u, so that would just be over u. And then notice, so this is gone. So notice that e to the x dx is right here. So we can just replace that with du. An alternative way to write this, maybe something you're more comfortable with, it's the same thing. It looks something like this, 1 over u du. Up to you how you want to do that. Okay, let's change our limits. If you plug in a 1, you get u equals 1 plus e to the first. So that would just be 1 plus e for that limit. Down here, if you plug in a 0, you get 1 plus e to the 0, which is 2. Okay, and 2 is less than 1 plus e, so I think we're good with that. So this would be, if we integrate here, we'd get ln of u, evaluated from 2 to 1 plus e. So that would equal ln of 1 plus e minus ln of 2. Okay, number 9 looks like a little application problem. So the particle moves along the x-axis such that the velocity is given by v of t right there. Find the total distance traveled. So let's at least set this up. Check this out. Yeah, we're going to have to use the calculator on this. This would be like on a calculator active section of a test or quiz. Let's just get a review. So total distance traveled, if you remember, is equal to the integral from a to b, whatever those limits happen to be, of the integral, the absolute value of v of t. So this is a pretty easy setup. Total distance traveled is equal to the integral from 2 to 4 of absolute value. And if you remember it, you can just write this as v of t dt. And I think maybe we'll evaluate this one. We'll figure out what the answer actually is, and we can kind of check, make sure that we've got it. Okay, so I plugged it in my calculator. I'm coming up with 31.4979. Gosh, I guess I didn't give you any units. This would be like linear units like meters or feet or something like that. Okay, I think that's it. That is it. So that's section 5.4. Make sure you have this mastered. Some good review problems in there too, involving some older concepts that are certainly worth you looking at.